Hey guys, welcome to another A-level further maths revision video. Today we're going to take a look at some more core pure revision, and we're going to take a look at the modelling with volumes of revolution. So the very last part now of this chapter, so we're basically looking at questions in context, nothing too crazy, just a bit of application. So let's take a look straight away at what we've got here. So these questions are never particularly exciting. Like you can see, we've just got this vase here. We've got an equation that we're using to model basically the curve. And what we want to find out is that basically the exact volume of water that can go in the vase. So let's have a go and see what we've got. So question 2 here. We're rotating it about the y-axis, so that's important, right? Because that means we're going to do this in terms of x. So remember the formula, v is equal to pi times the integral from a to b of x squared dy. Okay, so because it's about the y-axis, it's x squared dy. Now, it's already in terms of x squared, so that's nice, but you don't have to do any manipulation to get it in that form. The only thing we have to consider basically at this point is what are our limits. So the limits, well, if you read the question, we're told that the vase is filled to a height of 20 centimeters with water. So essentially we're going from 0 to 20, right? If we're filling this vase up with water. So we can write that then for our question here, that v is equal to pi times the integral here from 0 to 20 x squared, where x squared is 100y over 10y squared plus 1. Okay, so if I write that out, what we've got now is this integral here plus 1 dy. Okay, now very common again, like we've been doing for the previous volumes of revolution, we're going to use substitution to solve this integral. Okay, so if I sub in u, and I'm going to say it equal to 10y squared plus 1, right, the denominator here, because then we can differentiate it, get it in terms of dy as well, and we can start cancelling quite nicely. So u is 10y squared plus 1. So if we differentiate this, what would we get? We'd get du by dy, and that would be 10 times 2, 20. Take 1 off the power, so I get 20y. The 1 would just go to 0, so we'll just get left with 20y. So what we can do is we can work out dy as being du divided by 20y. Like so. Okay, so that's all quite nice so far. And at this point here, we just need to start substituting in. So v is equal to pi times the integral from 0 to 20, so from 0 to 20 of 100y, so 100y divided by 10y squared plus 1, but we know 10y squared plus 1 is u, so it's 100y divided by u, and we can then substitute dy here as du over 2y. Okay, so we're just transforming the variable that we're integrating with respect to here. Like so. 100y divided by 20y, that's just going to leave me with 5 over u du. Okay, so we can pull that 5 out to the front. So what's this going to give us? That's going to give us 5 pi times the integral of 1 over u, okay, between 0 and 20. So what I'm going to do is I'm just going to keep the limits as they are. Like I've discussed in a previous video regarding this, you can change the limits here, but I think it's easy just changing back to what our u is here, okay, at the very end. So 1 over u du, and this is just a standard result here, this is just ln u. So this is 5 pi ln u between 20 or 0 and 20, and don't forget u is 10y squared plus 1. So what we've actually got here is 5 pi ln of 10y squared plus 1, okay, between 0 and 20, so 0 and 20, and then at this point here we just need to sub our limits in. So we've still got the 5 pi on the outside, so 5 pi ln of 10 times y squared, where y is 20, so 20 squared times it by 10, and then add the 1, so we're going to get 4001, and if you put 0 in here, this just comes to ln 1, which is 0. Okay, so we don't need to worry about the 0. So we get 5 pi ln 4001. Okay, what units have we got? Well, we're working in centimetres here, so centimetres cubed. Okay, so in other words, we're told the form that it should come in. So we should get p pi ln q centimetres cubed. So we've got p here as being 5, and then the q is just 4001. So do it over here. So what have we got? P is 5, and then q is 4001. Okay, and there we have it. So there you see, nothing too crazy, nothing that you've really not done before, just a bit of context to it to try and make it a little bit more complicated, but nothing that you shouldn't be too put off by. Okay, so that's that question done. Next question here, the very next question actually, exercise 4D question 3. This time we're dealing with parametric equations, so makes it sometimes a little bit more complicated, but for this one, nothing too crazy. Part A, we want to prove that cos cubed theta is identical to 3 over 4 cos theta plus 1 over 4 cos 3 theta. So 3 marks for this identity. So the identity is not too bad. There's just quite a lot of working really for what is 3 marks. But let's have a look at it. So question 3a. So where do we begin with this identity and this proof? Well, the key part here is this cos 3 theta. Okay, so we consider cos 3 theta. Okay, cos 3 theta. This is the important part. Well, how could we rewrite that? Well, using the addition formula now here, we could write that as cos 2 theta plus theta. Okay, so cos 2 theta plus theta. I'll give you cos 3 theta, but at this point here now, we can use the addition formula. So, just using the result from your formula book here, so you don't need to memorise this bit. This would be cos 2 theta cos theta minus sine 2 theta sine theta. Okay, but I don't think that result's too difficult if you do want to just memorise it. So that's our first line of working. And now at this stage here, we need to take basically applications of the double angle formulas. So the fact that we've got cos 2 theta, sine 2 theta, it's very useful, right? We can use it. So cos 2 theta, we can write that as 2 cos squared theta minus 1 times cos theta. Okay, so this is just this part here. Minus, so 2 sine theta, sorry, minus sine 2 theta, sine theta. Don't forget sine 2 theta. We can write that as 2 sine theta cos theta. Okay, so in other words, this here now, we can write that as minus 2 sine squared theta cos theta. Okay, just making sure we've got this all correct so far. So at this stage now, we want to see if we can keep basically simplifying and see if we can keep working towards the required form. So at this stage here, I'm going to expand this left-hand part here, this 2 cos squared theta minus 1 times cos theta. So what would that give us? That would give us 2 cos cubed theta minus cos theta minus cos theta. And this sine squared theta bit here, we can use that as well. Again, another identity that you should be very familiar with. We can write that as 1 minus cos squared theta. Okay, so now this is minus 2 lots of 1 minus cos squared theta, like so, and then we times it by cos theta again. Okay, so as you can see at this point now, we've essentially eliminated the sine thetas here, and we're getting it all in terms of cos theta, which is what we should be working towards. So that's kind of the main idea here. So again, we can just keep simplifying. Just keep this part here as it is. So 2 cos cubed theta minus cos theta. So now minus 2 times 1 and then times that by cos theta, so that gives me minus 2 cos theta. Okay, and then minus 2 times minus cos squared theta would be 2 cos squared theta, and then times it by another cos theta, so we get plus 2 cos cubed theta. Okay, and then at this stage here, we just need to simplify. And don't forget, at each part of my working here, this is cos 3 theta. Okay, so cos 3 theta is equal to this. So just collecting like terms here now. The cos cubed theta, that will simplify to 4 cos cubed theta. And then minus cos theta minus another 2 cos theta will be minus 3 cos theta. Okay, so this is cos 3 theta. And the required form we want is cos cubed theta equals, or is identical to. So in other words, I need to rearrange for this part here. Okay, so 4 cos cubed theta is equal to cos 3 theta plus 3 cos theta. Okay, and then essentially we're there. Just to get that final bit, cos cubed theta is identical to this part here on its own. Just need to divide both sides by 4. Okay, so therefore cos cubed theta is it's identical to what we've got there. Okay, so 3 over 4 cos theta, and then a quarter cos 3 theta, yeah, as required. Okay, so like you can see, we've got exactly what we're asked to get. So like you can see, there's a lot of lines for it, but mathematically it's just using trig identities along the way. So hopefully that first part's not too bad. Like you see, it's quite a bit of working for 3 marks, but there we go. And then for part B here, so we'll just get rid of this, we've got the identity given. We need to now find the volume of the tent. So we're going to use volume of revolution here. Now, even if you can't do part A, don't be put off by the fact that you can't do it. You can still go on to do part B. So let's write in what we've got here. So x is 50 cos theta. Y is 30 sine theta. And where are we finding it about? So we're doing it about the y-axis, okay? So in other words, if we write out what the volume is, v is going to be equal to pi times the integral. So to get your limits here, sometimes you need to think about it. Sometimes, and like this example here demonstrates, it's easier than it looks. Consider the range of theta, so between 0 and pi over 2. So that's going to be our limit, so 0 and pi over 2, okay? So nice and easy. This will be x squared times dy by d theta. So because it's about the y-axis, we do it again in terms of x squared. We times it by dy by d theta, and this is all integrated with respect to d theta. Okay. So essentially, what we need to work out now is x squared and dy by d theta. So if we do that over here, x squared. So if you squared this term here, so 50 squared, and then cos squared theta here, so that's going to give us 2,500 cos squared theta. Okay, so that's nothing too tricky. And then dy by d theta, we just need to differentiate y with respect to theta. So if you differentiate 30 sine theta, what would we get? Well, hopefully a standard result here, just 30 cos theta. Okay, so we've got all the working that we need here. Now we just need to work out this integral. So it's pi times the integral from 0 to pi over 2 x squared. We know that's 2,500 cos squared theta times dy by d theta, which is 30 cos theta. Okay, times 30 cos theta d theta. Again, just simplifying here now, and then we'll eventually use this identity here. This is pi times the integral from 0 to pi over 2 of, so this would be 75,000, so 2,500 times 30 would be 75,000, but I can pull that out to the front, so actually let me just do that here. So we pull that out at the front, so we get 75,000 pi, and that's times the integral pi from 0 to pi over 2 of cos cubed theta d theta. Okay, so don't forget cos squared theta times cos theta get cos cubed theta. And then at this point here, this is why we're given part A. We can use this identity now to make this a lot easier to work with. So this you know, the 3 over 4 and the 1 over 4, I can apply this denominator of 4 to the front here. So that's 75,000 pi over 4 times this integral again. So that's basically now at this point 3 cos theta plus cos 3 theta. Like you can see at this point now, this is just a nice easy integral to work with. So again, do it term by term. So this 75,000 pi over 4 will remain at the front. Three cos theta, if you integrate that, what would you get? Well, you'd get 3 sine theta. Do the same with the cos 3 theta, but don't forget you're going to have to divide by 3 here. So this is going to be plus 1 over 3 sine 3 theta. So this is between 0 and pi over 2. Running out of room here. So between 0 and pi over 2. So we just finish it up here at the top. All I've got to do now is just sub in my limits. So if you do this correctly, you're going to get 75,000 pi over 4 times 3 minus 1 over 3. And if you work that out here, what you should get is 50,000 pi. And then if we put our units in, what we're working in, meters. So meters cubed because it's volume. Okay, so V equals 50,000 pi meters cubed. So like you can see, 5 marks for that, you know, and 8 marks for the question overall. You know, just be confident with your identities. Your trig identity is very, very important for this chapter. But moving on to the last question here now. Again, like you say, we've got quite another long, basically worded question. So again, another pretty boring one. It's another vase one, so they're not very creative, but we're given a diagram. We're told it's going between 0 and 4, and then we're given the equation of C. So it's this quotient here. So it's 5 divided by the square root of 1 plus 4x. Okay. Now, we want to find the volume here, the exact volume of the vase. So we need the formula for the volume of revolution. So that's V equals pi times the integral. So between 0 and 4, and don't forget we are rotating, what we're rotating it about the x-axis, yeah. So between 0 and 4. Okay. So this is y squared because it's about the x-axis, dx. Okay. Y squared, well, we've got y, so what we need to do is just square numerator, square denominator, we've got y squared. So y squared, that's going to be 25 divided by, if you square this denominator, you're just going to get 1 plus 4x. Just using your rule of indices there, so you get 1 plus 4x. So what I'm doing here now is pi times this integral from 0 to 4 of 25 over 1 plus 4x dx. And again, you should be used to it by now. Use substitution. So if I say u is 1 plus 4x, okay, if u is 1 plus 4x, we can work out du by dx. That's just simply going to be 4. And then simply dx will just be du over 4. Like so. Okay. So now we've got everything we need. Let's go back to our formula for the volume. So V is equal to pi times the integral from 0 to 4. 25 divided by u, because u is 1 plus 4x. And we know what dx is. Dx is du over 4. Okay, so du over 4. Now, this is technically 25 over 4u du. So what I can do, again using linearity, is plot the 25 over 4. And like I see, we're going to get a nice result here. It's going to end up with 1 over u again. So V is 25 pi over 4 times this integral of 1 over u du. Okay, so a nice result here. This is kind of what you're aiming for. This is very common but not guaranteed, but it makes it, you know, nicer to work with in exam conditions. So this is going to be 25 pi over 4. 1 over u, remember, that's ln u. This is ln u between 0 and 4. But we know what ln u is because we know what u is, so that's 1 plus 4x. So we can write that as 25 pi over 4 times ln of 1 plus 4x. Like so. Okay. So all I need to do now is just plug my limits in, right? Again, if I put the 0 limit in here, I just get ln of 1, which is 0. So don't worry about the 0 limit here. Just consider the 4. Okay, so that's going to be ln of 17. So this is 25 pi over 4 ln 17. Okay, but be very, very careful. The question's not quite done here, and the reason for that is because, and this is what I recommend for all these questions, read it very, very carefully. We're told that each unit on the axis represents 2 centimeters. So we're actually using a scale factor here now. So just to finish with, we do it up here. So using a scale factor here. So if one unit is 2 centimeters, then the volume, we need to times it by 8 because it's 2 centimeters cubed. Okay, so 8 essentially, that's the scale factor there. So 25 pi over 4 ln 17 times 8. So 25 pi over 4 ln 17 times 8. So the 4 is going to cancel there with this to bigger 2, and then 25 pi ln 17 times 2. So we get 50 pi ln 17. Okay. So we've got it in the form they asked for as well. So A in that case is 50, and then B is just 17. Okay, so I won't bother writing them down, but you can just deduce that yourself. And then for part B, just one reason why the volume of the vase might actually be less than the answer that we've got. It's just a one-liner basically. If we do it up here, so B, just one reason. Basically, you can just say that there's non-zero thickness of the vase. So non-zero thickness. That's simply all we've got to say there. Okay, but that brings us to the end of that question. And that actually brings us to the end of this video. So I hope it's helped. It's, you know, I quite like this chapter. It's quite an enjoyable one. But if there's any mistakes through here, please just let me know down below. And if there's anything you'd like me to go through, again, just let me know down below. Cheers.